So we have Akshit Bhalla here.
Sure. All right. So Akshit is here. Akshit, welcome. Welcome to Odin Talks. I look forward to hearing what you want to say. So let me give you a little background about Akshit. And Akshit, I would like you to introduce yourself in a lot more detail. So Akshit is a data scientist with a wealth of knowledge and experience. He has worked in the HP labs for some time with a lot of experience. He also has knowledge and experience on the AWS side, Azure side. He has worked on several ML platforms. He has worked on big data apps, and he has worked as well on deep learning applications. So it's a very wide experience Akshit has. So with this, Akshit, welcome to Odin Talks, and I would like you to introduce yourself in a lot more detail.
Thank you so much for introducing me, Vijay. So as he mentioned, I'm currently working as a data scientist at HP Inc. Bangalore. I work with the customer support team. Basically, you've all contacted some customer support at some point, right? Wherein you want to have some queries clarified or ask some questions. So HP also makes products and people have questions about these products, so they contact us. So these operations are optimized using data science. That is what I do. So apart from that, in my personal life, I like to play basketball and I also enjoy gardening. I look forward to interacting with you all today. Shall we get started with the presentation then?
Yes, Akshit, you can start. Yes, please start, Akshit.
Yes. All right. I hope my screen is visible to you all.
Yes, Akshit, it's perfect.
All right. So as I mentioned, my name is Akshit Bhalla. I'm a data scientist at HP Inc. I'm also an incoming Master of Data Science student at Columbia University, New York. Today, I will be covering a rather advanced topic on object detection. This will be an introductory class wherein I will be covering topics right from water images to how object detection happens in the real world. If time permits, we will also go over a code example of how things are implemented hands-on. So before I begin, I would like to thank OdinSchool for having me today. It is a pleasure interacting with you all today. All right, let me get started. Yeah. So first, I will be talking about what are images. I will be introducing images. Let me see if there is an annotation option here. All right. So for the purpose of this class, although it is an introductory class in an advanced topic on machine learning, I would assume that you know very basics about what is classification, what is regression, what is Python, very extreme basics of these things. If you have that knowledge, then I can assure you that this class should not be very intimidating. It should be very simple and straightforward for you to understand. You know, when I was starting out learning all of these, to be honest, I do not have a background in computer science or, you know, any of these advanced topics. But if I was able to start out, make great progress, I'm sure you guys will also make great progress in this field. So don't feel intimidated by any topics that we will be covering today. Just learn, explore. If you have any questions, I would be happy to answer them. So first, we will be covering water images. I will be introducing images. Then we will be covering certain applications of images. Next, we will look at how we can perform certain tasks such as classification and regression when we have images. With this background, we will be able to understand how object detection is performed. With some theoretical understanding, we will be able to understand how to implement everything in code. Okay, I'm not sure why that's happening. Okay. So let me quickly erase all of this and move to the next slide. All right. So here, as you can see, I have certain images, right? Let me go over them one by one. Firstly, what is an image? What are images? So all of us were born in the age of, technology, wherein all of these technologies seem very natural to us. We think, hey, you know what? We already know what an image is. It's something that we see on our phone, something that we can use a camera and click. So we think of them as that. We never think about how they are actually stored, how they are actually produced, how they are actually, made use of, or transmitted, and so on. So today we will try to understand how images are actually represented in the background. So basically speaking, what is an image? It is a visual representation of something. If you take out your phone, you click an image, what is it? It is a visual representation of something, right? So that said, what is it in the background? You see an image on your phone, but how is it stored in the background? In the background, it is actually stored as a matrix of numbers, right? It is stored as a matrix of numbers. So as you can see over here, a matrix of numbers. So how do we go from an image to a matrix of numbers? Let's understand. So here on the very left, I have an image. It is a 16 cross 12 image, by which I mean 16 in height and 12 in width, right? We have this image over here. Now, although I do not very clearly see what is there in that image, I can roughly say that this is Abraham Lincoln. I know that because of the way in which the cells in this grid are colored, right? Such as you can see, there is only black, white, or gray in this image, right? And such an image is called a grayscale image, right? The colors in the grid, are in such a way that I can tell what that portion represents. Like this represents a face, and it is definitely Abraham Lincoln. If I had a bigger grid with many more cells, the image would be more finer, and I would be able to see the face very clearly. Okay, this is a rather zoomed in picture. So this is a grayscale image because it has just three colors, actually just two, black and white, and anything between black and white, a mixture of black and white. So if you could represent these colors, these gray intensities as numbers between 0 and 255, you will get a matrix. So as you can see in the next image over here, instead of the, actually not instead, along with the pixel intensity, along with the pixel color, we also have a measure of intensity, right? Like we can see that this intensity is 157, this intensity is 153. These are shades of gray, degree of grayness or degree of blackness, right? Or degree of whiteness, I should say, because the higher the number, the more it will incline towards white. If it is 255, it is completely white. If it is 0, it is completely black. So higher the number, the more whiter it gets. Lower the number, the darker it gets. So in that manner, we have these numbers representing, the intensity of each cell, right? Now let's look at the third image now. Now remove the colors, forget the colors. We will only work with this matrix here, which is a 16 cross 12 matrix of pixel intensities. That is all we need. All the magic happens using these numbers. Your phones, your laptops, all these devices actually have these numbers in the background. When your phone or laptop wants to produce images, it actually uses these numbers and produces that much intensity on your screen, which you interpret as an image, right? Then on the rightmost here, as you can see, we have twin tower, right? We have two towers, right? Twin tower. And if you take a very small section of this image over here, you will see that, these are actually numbers. Let me move this panel aside. You will see that these are actually numbers. It's a pixel intensity value. So with this basic understanding about what are images and how they are stored, let's move on to the next topic. Able to move to the next slide. Yeah. Okay. So that was about grayscale images, but more often than not, you guys have encountered color images. Now, how are color images stored? Now, how are they represented? Basically, it is easy to produce black and white images because, white light, if it is absent, it is black. If it is present, it is white. Anything in between is gray. But other colors that computers can comfortably produce are red, green, and blue. And scientists and researchers and engineers have found that a combination of red, green, and blue can produce any color. So basically, color images are essentially three images, one behind the other: a red image, a green image, and a blue image, right? In this fashion. Okay. And each of these images are themselves matrices. When you overlay these matrices with their respective intensities, they actually form color, right? So although the numbers that you see in the red matrix, green matrix, and blue matrix are very small, between probably 0 to 50, I can't see a bigger number. In practice, these numbers are generally between 0 and 255. Okay, there is no such rule about how high or low these numbers can be. Normally speaking, it is like that. And for the purpose of this lecture, it will be like that. Okay, so when you overlay a red filter on a green filter on a blue filter, what you get is a color image. Okay, also called as an RGB image, because there are many other ways of representing images. Okay, so this is how color images are represented. Next, let's look at certain applications of images. That is, what can you do with these images? So one task with images is classification. If I gave you chest x-rays, okay, of people, and I told you, hey, you know what? Tell me which people have COVID and which people do not have COVID, right? You would, try to segregate them into groups. Such a task is called classification. And because we are dealing with images, it becomes image classification. In this particular example over here, sorry, let me use the eraser. Yeah, in this particular example over here, in image classification, we have images of cats and dogs. If I gave you 100 images, each image either having a cat or a dog, and I told you, hey, you know what? These are some pet animals that I have, and I want you to tell me which one is a cat and which one is a dog. So such a task would be image classification. There is a more, I would say sophisticated task, which is called object detection, which is the topic of today's lecture, right? What happens in object detection is, I will give you an image and you have to tell me what is there in that image. It could be a cat or a dog or something else, but also you have to tell me where it is located. In classification, we only say what. In object detection, we also say where. So in object detection, we tell where in the image is the cat located, dog located, and so on, right? We indicate that with these bounding boxes. Okay, that's how it's done. Then there are certain more advanced tasks, like you see this image of a cat right here, right? You see this image here. Now, in this image, I can see that there is a sky, right? This portion is the sky, right? And this portion, of course, is a cat. Okay. At the bottom over here, I can say that, all of this is grass. And in between, whatever is there over here is actually trees. So if I gave you this image and I said, hey, you know what? Identify the cat, identify grass, identify the sky and trees, identify all of those things and tell me where they are, then such a task would be called as image segmentation, wherein you are segmenting every bit and piece of object in that image. How is this useful? Where is the application? For example, if I gave you chest x-rays of certain people and I told you, you know what, some of these are infected x-rays, the chest x-ray, some of them are diseased. There is a problem with those x-rays, but other x-rays are there which are normal. So given this information, can you segment the area that is affected in the chest? Can you tell me which is the affected portion? So such applications are real world applications. Then let's say, for example, here, okay, you are going in a car and you happen to click a picture and the picture is blurred. Okay, is there a way to make the picture non-blur? Can you de-blur that image? Yes, you can. That task is called de-blurring. Okay, and there are certain very advanced tasks wherein you are mixing and matching a number of, data modalities. Like here we are discussing only image, right? There are other modalities like text. There are other modalities like some tabular data and so on. Voice, voice. There are other modalities. So certain applications mix and match all of these modalities, and those are very advanced applications. I will cover just one of those, which is image captioning, okay, wherein we deal with images and text. So if I gave you an image and you had to upload it to Facebook or Instagram, and Facebook and Instagram automatically told you what is there in that image, right? It captioned the image for you. Such a task could be image captioning. As you can see at the bottom right over here, if I put this image in a image captioning software, I will get this as the output. Man in black shirt is playing guitar. Okay. Image is the input, text is the output. So this is a slightly more advanced topic. Okay. And there is also another task called image registration here. For example, you have a satellite that takes images of certain area. Okay. It takes one image and then it moves slightly at an angle and then takes another image. Okay. Now, because it has only moved slightly, there will be a huge overlap in what is there in both the images, right? There will be some new information also, but it will mostly be the same information that will be overlapping. So if I gave you these two images, if you see closely, this image here on the left, this orange color image here is slightly rotated. Okay. And this on the right side, this image that I have, this gray color image, this is, let's say, in place. This red one is what is rotated. Then how will you rotate the first image so that, it overlaps the section in the first image? How will you rotate the second image to overlap the area in the first image? Such a task is called image registration. Okay. For the purpose of this class, I will not go into any more detail. I will be covering only object detection. Right. So let's dive into this particular application. Okay. So before we move on to the next topic, I would be happy to answer any questions. Sneha, if you want, I can take up questions later also, if you guys are answering questions in chat.
Akshit, there is one question.
Yeah.
Is object detection used by CAPTCHA feature 2?
Is object detection used by CAPTCHA feature 2? See, in CAPTCHA, as far as I have worked with CAPTCHA, you are asked to select something like planes, something like, boats, something like that. And you select those images. But you don't select where in that image is the plane located, where in that image is the boat located. So that is just merely classification, not object detection. I hope that answers the question.
Yeah, and one last question is, what is the main purpose of object detection?
So the main purpose of object detection, see, object detection is like, a collection of techniques to identify where in an image an object is present. Okay. Now, this is the objective of object detection. Where is the application, if you ask me? How is this useful? Why are we trying to do this? Like I said, for example, I gave you a video footage. Okay. And I told you that this is the video footage of a store. Okay. Where things are sold, groceries maybe, for example. And I tell you that you have to identify using this footage every thief. Anybody who's a thief, you have to identify. The moment that person, slides something into his pocket, or maybe, without purchasing tries to leave, you should be able to identify that person immediately. How would you do that in real time? In that case, you may not have a person sitting over there and monitoring all the video footages throughout, correct? In that case, you need some sort of an automated system that can automatically identify thieves in the video footage, correct? So you will have people, the moment they put something in their pocket, if you display a box around such a person, and the moment a box appears, an alert is raised, that can help reduce, pilferage and, things of that sort in grocery stores, for example. And I gave another example of, healthcare, wherein, let's say you have healthy images, healthy chest x-rays, and also, diseased chest x-rays. And I tell you, hey, you know what? Identify the region, localize the region where the chest x-ray is diseased. Like you may have some pneumonia, you may have some other COVID-19, some sort of disease, right? So identify where in that lung is that disease located. So that is also another application of object detection. So that is why, object detection is such an important thing. I hope that answers your question.
Yeah, Akshit, please go ahead with the next topic.
All right. Okay. So now let's come to the topic of convolutional neural networks for classification and regression. So for the purpose of this class, I would assume that you have some knowledge about, what is a neural network. If you don't, I will just cover it briefly so that you do have an understanding. So if you have, let's say, a number of inputs, let's say x1, x2, x3, some number of inputs, and you want to, map it to some sort of an output. Like, let's say the output is binary, in which case you want to produce either 1 or 0. Okay, 1 or 0 can be your output. So what happens in neural networks is if x1, x2, x3 are your inputs, right? You feed it into the neural network, okay? And the neural network basically has a number of nodes, okay, that are interconnected with each other. They are interconnected with each other. And finally, at the output, you have either a 1 or a 0, okay? Given this input, the neural network is able to spit either a 1 or a 0. So let me give you a more practical example. Let's say that I give you 3 inputs, okay? A person's age. I don't know why this is happening like this. Okay. I give you 3 inputs. X1 is age, a person's age, okay? I give you his height. I give you his age, I give you his height, and let's say I give you maybe his blood pressure. Okay, X3 is blood pressure. I give you these 3 details. And or maybe not blood pressure, a more better example would be gender. Okay, male, female. Okay, male/female. Let's say these are 3 inputs: age, height, and male, female, gender. These are 3 inputs. Given these 3 inputs, can you identify whether this person is overweight? If this person is overweight, produce 1, otherwise produce 0. So this would be like a binary classification using neural network. So classification is not the only thing that neural networks can do. In classification, like you're producing numbers like 0 and 1, right? You can also produce 0, 1, 2, 3, like buckets. But that is about classification. But neural networks can also do something called regression. In regression, instead of a number like 0, 1, 2, 3, you produce a float, you predict a floating point number. Okay. For example, if I give you age, height, and male, female, okay, the neural network will take these as input and it will produce an output of, let's say, 0.8. That is the degree of healthiness. 0.8 is the degree of healthiness. This number can be, let's say, between 0 and 5. Now, if you get 0.8 as the person's degree of healthiness, you obviously know that this person is not very healthy, right? So this number could have also been, let's say, 4.8, in which case it would be a very healthy person, right? So if normally speaking, in general, to put it simply, in a neural network, basically you have some inputs, and if you have the output as, a category, present, not present, cat, dog, human, something like that, categorized, in that case, it is called a classification problem. And if instead of a category, you have a number that is outputted, like the degree of healthiness, or maybe you are trying to predict somebody's age. Okay, age is also a number, right? So that also you're trying to predict. If you're trying to predict any number, temperature, something like that, in that case, it is called a regression problem. Okay, wherein you are trying to output continuous values. Okay, so that said, I will now begin with what a convolutional neural network is. A convolutional neural network is something that uses images as input to perform classification or regression. Okay, we will look at both classification and regression because both are important for object detection. So let me clear some things here. Okay. Now let's look at convolutional neural networks for classification and regression. But before we understand how a convolutional neural network works, we have to break down each element and understand it individually. So first, let's understand what is a convolution. First, let's understand what is a convolution and how it is used. It is used in edge detection. Then let's understand another topic called pooling. With having understood convolution and pooling, we will look at how is a convolutional neural network constructed. Once you have understood how a convolutional neural network is constructed, we will look at how it is used for classification and for regression. So first, let's look at what is convolution. Okay, so what is a convolution? Let's say that you have an image. In this case, I have a very small image, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, a 5 by 5 image. I have an image that is 5 by 5. Okay. Let's say, for the sake of argument, that, okay, this image has only one channel for now. Okay. It is a, let's say, black and white image. Okay. It does not have many channels. It is a black and white image. So there is only one matrix here, 5 by 5 matrix. Okay. In color images, since there are 3 channels, it will be 5 by 5 by 3. But since this is a black and white image, for argument's sake, we will say it is a 5 by 5 image. You can say it is a 5 by 5 plus 1 image because there is only one channel, black and white. That's all. Now, just for understanding sake, assume that you have a 3 by 3 matrix over here. You have a 3 by 3 matrix over here. Now, this 3 by 3 matrix has some numbers in it. You know that numbers in this image over here represent pixel intensities. But the numbers in this image, for now, assume that they do not represent anything. They are just there somehow. Okay. Now, that said, we will look at what a convolution operation is first. Okay. We will look at what a convolution operation is. So take this small 3 by 3 matrix, okay, and put it over here. Okay. When you do that, 2 and 1 will overlap, 4 and 2 will overlap, 9 and 3 will overlap. Again, 2 and minus 4 will overlap, 1 and 7 will overlap, 4 and 4 will overlap, and so on. I'm sure you got the idea. Okay. When that overlapping happens, what I want you to do is I want you to multiply the overlapping numbers, which means you will multiply 2 and 1. So you get 2 into 1 is 2. When 4 and 2 overlap, you get 4 into 2, 8. Add it. Then when 9 and 3 overlap, you get 27. Add it. Plus 2 and 2 are overlapping. 2 and minus 4 are overlapping, sorry, you get minus 8, and so on. You keep doing this until you have added all the 9 numbers present over here. Okay. When you do that, you will get 51. Okay. After you have done that, what I want you to do is, I want you to place that 3 by 3 matrix over here. Slide it by 1 unit to the right. Okay, slide it by 1 unit to the right. And do the same thing again. Now you will get 66. Okay. After you get that, slide it once more. In that case, you will put it over here. Okay. And you will get some number over here. When you have done that, slide it downwards. Okay. When you have done that, slide it downwards. So you will place the matrix over here. 3 by 3 matrix will come over here. And you will again multiply those numbers and you will get some number over here. Okay. So this operation that we just performed is called a convolution. Okay. It is called a convolution between 2 matrices, in which case one of the matrices is a image. And this other matrix, don't worry about it for now. What are those numbers? Just understand that this is a convolution operation. Okay. All right. So one key thing that you should notice over here is we started out with this image. Okay. And as the output, we got this small matrix over here, which is also an image. Okay. But it is much smaller. This was 5 cross 5. This is 3 cross 3. Okay. Now, how did it become smaller? You must have noticed that in the process of sliding, okay, then it becomes smaller. We will not go into the complete math of how this is happening, but this is a key takeaway that the image becomes smaller when we perform convolution. Okay. That said, now let's move on to the next topic of pooling. Okay. Sorry, before we move on to pooling, I want to cover this in slightly more detail. Okay. So how is this useful? Now we were talking about convolution and all that, right? How is that useful? Basically, scientists and researchers have found that if you have a 3 by 3 matrix like this, okay, and the numbers are in a certain way, like we have -1, -2, -1 in the first row, then we have 0, 0, 0, and then 1, 2, 1. These are numbers in a specific way, right? When we have numbers in such a specific way, and then we apply convolution, we are able to detect certain patterns in the image. So when we multiply this matrix with this image, we get edges detected like this. Okay. So this is a very profound discovery. So this is why we perform convolutions, because convolutions enable us to discover patterns in the image. Okay. Now let's move on to what is pooling. Okay. In pooling, what we do is, now let's consider that you have another smaller 3 cross 3 image over here, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. You have a small 3 cross 3 image over here. In pooling, what you do is, more specifically, 2 cross 2 pooling. Okay. In 2 cross 2 pooling, what you do is, you take the first 2 by 2 section of this image and you take the highest pixel intensity, in which case it is 4. Highest pixel intensity is 4. So you will write it down here. Then what you do is you slide it another time towards the right and you take the 2 cross 2 section over here and you identify the highest intensity pixel, which is 5. After you have done that, move downwards. Then you will place it over here. Between 3, 4, 6, and 7, the highest pixel intensity is 7. And lastly, between 4, 5, 7, and 8, the highest pixel intensity is 8. This is called 2 cross 2 max pooling. Okay. Now, why is this done? Basically, if an image had all zeros, all black, it conveys no information. When there is white, the more sort of white there is in a certain region, that region is conveying some information. So in a small segment, we are capturing that bit of information by considering the maximum pixel intensity. So this is why we take the maximum value. And why do we take only 2 cross 2? Why not maybe 3 cross 3, 4 cross 4, something like that? We can. But it is more common to take smaller matrices because they work well, right? It is more fine-grained. Now, with that said, let's move on to the next slide and try to put it all together and try to understand how convolutional neural networks work. I had earlier described neural networks, right? Now, this bit is your neural network. Okay. This is your neural network. As I said, in neural networks, you get some input, x1, x2, x3, you have some input. Okay. Then they are mix and match together, one layer after the other. And by the end, you can have some sort of prediction. Let's say in this case, we have 3 outputs. Sorry, let me erase that. In this case, we have 3 outputs, 1, 2, and 3. And we are trying to predict whether this input image, this input image over here is a horse, zebra, or a dog. That is the objective. This is a classification task. Okay, we are looking at classification first. So let's see how convolutional neural networks perform classification. Given this image over here, I know that it is a zebra. But how can you train a neural network, a convolutional neural network, to identify that this is a zebra? So if I gave you, let's say, 300 images, 100 zebras, 100 horse, and 100 dogs. And I told you, you know what? These 100 are zebras, these 100 are dogs, and these 100 are horse. You can train a convolutional neural network that takes inputs and outputs and learns the mapping. It takes zebra and learns to map that this is a zebra. It takes a dog and learns to map that this is a dog. It sort of learns to do that. Okay. Sometimes, images can be confusing also, right? If you pass like a dog, it can think that it is a horse. So there is some degree of classification also. So to be more specific, to be more specific, in the output, the neural network says it is a zebra with a probability of 0.7. It is a horse with a probability of 0.2, and it is a dog with a probability of 0.1. Okay. So it does not entirely say that this is a zebra, but it will give you some probability, 0.7 probability that it is a zebra. So since that is the highest probability, you can say, okay, this must be a zebra only. Okay. So this is how prediction works with the neural network. Okay. It takes certain inputs from this left half. That input is fed into the neural network. Okay. That input is fed into the neural network, and this neural network makes the prediction. But first, let's now look at the left part about the convolution part. Okay. It is called a convolutional neural network because there are convolutions on the left and neural network on the right, if you can see, right? There are convolutions over here and there is a neural network over here, convolutional neural network. So in convolutional neural network, you have this image over here. Okay. You perform convolution as discussed in the previous slide. Once you perform convolution, that image becomes smaller. Then on that image, you perform pooling, right? Then that image you perform pooling, it still becomes smaller. Okay. Then on that image, you again perform convolution and pooling, it still becomes smaller. Again, you perform convolution and pooling, it becomes still smaller. You keep performing these operations one after the other until you are left with a matrix with just one element. So by the end, by the time you reach this point, you will have a number of matrices, right? One matrix behind the other, like this, you will have many matrices. Each will have some number over here. This can be 0.8, this can be 0.7, this can be 1, this can be 0, this can be maybe, I don't know, maybe 1.3. It can be something like that. Okay. From left to right, as you go, the images become, the image that you took as input becomes smaller and smaller. By the end, you get matrices one behind the other with just single element, and that is then fed into this neural network. Okay, that makes some prediction about whether this is a horse, zebra, or a dog. I know this can be a little confusing and a little intimidating. So if you have any questions right now, I would be happy to address them, because moving forward, you would need to know slightly more details. So it is better to address questions now. Any questions from your team? If you want, I could go over convolutional neural networks again for more clarity.
Akshit, there is one question.
Yeah.
How pooling will select the grid?
Pardon me?
How will pooling select the grid?
You mean in the previous examples, like we took these numbers during convolutional neural network, like how does it know what numbers to take? Is that the question?
Yeah, this is a question from a student. So,
okay, that is a good question actually. That time when I was talking about convolution, I said, hey, you know what? In when you perform convolution and the small matrix, which is also called a kernel, when that takes specific numbers, like we saw here, when it takes specific numbers like -2, -1, -1, -2, -1, 0, 0, 0, 1 to 1, in that case, we can identify edges, right? When we perform convolution and pooling once, we can identify edges. Okay, great. When again on that image, we perform convolution and pooling, we get some more patterns in the image. The more convolution and pooling you perform, you identify deeper and deeper patterns present in that image. That is the logic. Okay. But the question here is what are the numbers present in those kernels? Like here we have -1, -2, -1. What are the numbers present in those kernels? The truth is, this is called machine learning because those numbers are learned during the training process. So I did not cover details about backpropagation and things like that, which is slightly more advanced. But what happens is initially the convolutional neural networks starts with a kernel that has random numbers in it. Like here we have fixed numbers, right? -1, -2, -1. We know that if we multiply this matrix, we will get edges. But maybe the pattern in the image is not just related to edges. Maybe it is related to something else. So edges, we know we can identify using that kernel. But what if there is something else we need to predict, right? But what if there is something else other than edges? In that case, we just leave it to the neural network to figure out what it has to extract from the image. So the kernel numbers, the numbers inside the kernel are random at first. And as the neural network learns iteratively, those numbers are updated to reflect, a certain pattern with respect to those images. I hope that roughly answers your question. If it does not, I would be happy to understand your question better.
Yeah, thank you, Akshit. So let's continue with the rest of the session.
All right. So having understood classification, let's summarize this classification bit before we go to the next topic. So what we just saw is that we have a zebra image as input. Okay. It is fed into a convolutional neural network. Okay. And that convolutional neural network predicts, okay, what is that image about? Is it a horse? Is it a zebra? Or is it a dog? And it predicts that with a certain probability. In this case, it is 0.55 highest probability, so it has to be a zebra. This is the takeaway that I want you to have from this discussion. In classification, in image classification using convolutional neural networks, you have an image, you have a convolutional neural network, and the output of that convolutional neural network is what is present in that image. Okay. The convolution and pooling in this whole stuff that we just discussed over here, it does not always have to be in that way. In fact, scientists and researchers have been trying to and are still trying to identify newer ways to, perform convolutions and pooling in more complicated and more sophisticated ways to do the same thing. For the purpose of this, discussion, I want you to take away that in image classification using convolutional neural networks, you have an image, you have some sophisticated architecture that performs, a prediction, and then you have the prediction. Image, convolutional network, and output. Okay. That said, let's move to object detection. Okay. That said, let's move to object detection. Now, I give you this image over here on the left, and I ask you, hey, given this image, find where are the zebras. So far, you were able to tell me if there is a zebra or not. Now, I want you to tell me where is the zebra. So in object detection, that is the task, wherein you identify what is present as well as where it is present. So if you give me the correct answer would be like this. There would be a box around the zebras. Right? In this red color box that you see in this right image over here, right? So in object detection, what we do is localization. Where is the zebra in this image? And, in the process of making a prediction, like the neural network predicted that the box is present over here, right, in red. It is also possible that the neural network makes multiple predictions about the boxes. For example, it could say that the zebra is present over here. Okay. Now this orange color box and this red color box essentially refer to the same zebra. Let me draw another box. Okay. This is a green color box. This green box, red box, and orange box, they all correspond to the same zebra. And that is not what we want. We just want one box, whichever is the best box. Not even going to go into the details of how to identify the best, but whichever is the best. So this technique called non-max suppression is what helps us with that. Non-max suppression basically suppresses outputs that are not the best, which are non-max suppression means it will select the maximum probability box as the correct box and the others are suppressed. I will get into more detail as we move forward. So these are two topics that I'll be covering in object detection. Okay, let's move on to the next image. So you must be familiar with this image that we were discussing previously. wherein we perform convolution and we perform pooling one after the other. And by the end, we have matrices with single elements. Like there can be a 1 here, there can be a 0.5 here. I'm not sure why the annotation is behaving that way. Okay, but anyway, you will get numbers like these. Okay, and these numbers are then fed into the neural network that performs classification over here. But that is one thing that we want to perform. There is also a second thing that we want to perform, which is regression. This time we also want to localize and not just classify. So if we want to localize, we also want to know where in this image, this is a zebra. We also want to know where in this image, right, is the zebra present. Sorry, the green one is not where the zebra is present. This is wrong. This red box that you see here is where the zebra is present. Let me annotate that again. Yeah, this red box here is where the zebra is present, right? This red box that you see here, this is where the zebra is present. So we not just want to know what is present in this image, but also where it is present. So what we do now is, as before, we perform convolution and pooling from left to right, okay, to perform classification over here. But this last but second layer, okay, this last layer, as you know, it performs the classification. It tells you whether it is a horse, zebra, or dog. But this last but second layer, its input also goes into another second output. Its input also goes into second output. Okay. These will again be connected to this also. For simplicity's sake, it gets messy if I try to draw everything, but I hope it's understood. So this last but second layer also gives information to another output. And that other output is actually basically giving information about where in the image the object is present. Let me show that with an example. So here in this image, as you can see, it is a, let's say, 50 by 50 image of a zebra. 50 by 50 image of a zebra. Okay. In this image, if I start from top, this is x-axis. Oh. Then this is x-axis. Not sure why that's happening. This is the x-axis, right? And this is the y-axis, right? In the coordinate system with images is slightly different. We measure x from left to right and y from top to bottom. So let's say that, this is x height 5 measurement of x, and this is 45 in height. Okay. Y is equal to 45 here and x is equal to 5 here. This is how we measure coordinates in images. Okay. That said, given that coordinate system, we identify what is the top left box in the image. We identify the top left box coordinates in the image and also the bottom right coordinates of the box. So we were given images and we were also given where in the image the zebra is present. So when we say where in the image the zebra is present, what we essentially mean is the top left bounding box coordinate and also the bottom right bounding box coordinate. We have this information with us. Okay. Once we have this information with us, we give that as the output to the neural network. We say, hey, you know what? Top left is 5. We say, hey, you know what? Top left y is 45. As you can see, 5 and 45 over here. Then we say, hey, you know what? Bottom right x coordinate is 50. Bottom right y coordinate is 10. As you can see, 50 and 10 is present over here. Okay. We give this information, and just like we were training for classification, right? We train for regression also simultaneously. This neural network is a single neural network that performs classification and regression at the same time. The classification tells us which animal is present, and the regression tells us where it is present. To keep things simple, this is how classification and localization work hand in hand. Do we have any questions here? If you want me to say it in slightly more detail or cover a different topic, I would be happy to address your questions. All right, I will take that as a no. Okay, so let me, yeah. So now that you know that, we can perform, if I gave you a 50 by 50 image, if I gave you a 50 by 50 image, you know that you can perform classification as well as regression. You can identify in that 50 cross 50 patch, is a zebra present or not, and you can identify where it is present. With that information, let's see how object detection is performed. In object detection, what we do is we can have images of any size. So this image is obviously not 50 by 50. Height and width are not equal, as you can see. What we do in object detection is we have the image and we divide that image into grids. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have a 9 cross 14 grid that is overlaid on top of the image. Okay. And in this 9 by 14 grid, what we do is we decide that we are going to consider sections of size 2 cross 2. As you can see, this orange bounding box over here, right? This orange bounding box. We have decided to use, regions of size 2 cross 2. We are also going to use regions of size 3 cross 3 as denoted by the yellow box over here, as well as regions of size 4 cross 4 as denoted by the red box here. Now what we will do is, you remember in convolution and in pooling, we were moving from left to right and from top to bottom. What we are going to do with these sections is we will move these sections, all three of them, from left to right and then from top to bottom. We will do the exact same thing. So when we move this orange box, over here, it will be present over here. Then when we move it to the right, again, it will come over here. When we move it again to the right, it will come over here. Okay. And each time that box is moving, every time that box is moving, you get a small sub image or a patch of that image, a small section of that image. That section of that image is also an image, correct? So when you have a small patch of the image, let me laser pointer. Okay. So when you have a very small patch of the image, like this red color patch, yellow patch, or orange patch, that patch could be over here. It could be over here. It could be over here. So as that patch moves along the image, at one point or another, the zebra will be captured in a square image, right? That is what we're trying to do. Basically, as these orange, yellow, and red boxes move across the image, we get sub images of, fixed dimension. Each of those sub images goes into this classification and regression neural network. Each of those sub images go into that classification and regression neural network, and we identify whether in that subsection zebra is present or not. So these boxes will keep moving from left to right and from top to bottom. The moment the box is present over a zebra, that box, when it is fed into the neural network, it will be able to output whether a zebra is present or not, as well as where it is present. So that is the objective of, that is how object detection is done. That is one way of doing object detection. Of course, there are many others. So in this manner, we can perform object detection. And of course, it could be the case that, let's say I use this red color box. It could be the case that the zebra was detected over here, 3 cross 3. And again, maybe in 4 cross 4, it was detected over here, 4 cross 4. It is possible. But I do not want this box and this box. I don't want both boxes. Similarly, there could be many other boxes. There could be another box here also, right? So a technique called non-max suppression is used to identify which box to select. Basically, every time a prediction is happening, as you can see, every time a prediction is happening, there is a probability associated with the animal, right? So here, if it is telling that if in the top box it is telling that the probability of zebra is 0.8, next box it is telling me that it is 0.7, third box it is telling me that it is 0.75. You obviously know that the 0.8 box for the zebra is the one with maximum probability. So you will go with that. Okay, you can suppress all the others in some manner. Basically, that is how non-max suppression works. But that is just the first step. In more detail, actually, what happens is there is some region of overlap, right? Let's look at this example here. It is a better example. Here, there are 3 boxes surrounding the zebra. When we were performing that operation, right, wherein we are moving the box from left to right and top to bottom, we are getting sub images, one image, next image, next image, next image. In each of those images, we were able to predict whether a zebra is there or not and where it is present. But as a result, we got multiple zebra detections for the same zebra. So each of these boxes have some overlapping region, right? There is a huge overlap. As a first step, what we do is we take the most probable one. Chances are that, not most probable one, let's say that we take all those boxes that have probability of more than 90. Okay, if we do that, then only this red color box will remain. But we don't know in advance, right, what the probability threshold should be. So maybe we take prediction threshold of let's say 0.7. Okay, if we take 0.7, in that case, we are left with all the 3 prediction boxes. But which one to take? We use threshold, and in that manner, we were able to, suppress maybe 10, 15 other bounding boxes. But now that we have 3 bounding boxes, how do we identify the best one out of these 3? For that, we use something called IOU, intersection over union. Okay. In intersection over union, what we do is we firstly keep our hand on the most probable box. These 3 boxes remain, right? All the others were suppressed. Out of these 3, 0.95 is the highest probability. So just hold that. That is called the anchor. Now, with respect to that box, find the overlap of all other boxes. So with respect to the red box, find the overlap of green box. With respect to the red box, find the overlap of orange box. When you find the overlap, you find the overlap divided by the union and you get a number. Correct? Again, you should put a threshold on that number. If there is a huge overlap, then suppress those boxes. If there is no overlap, then maybe it is a separate object. So this can be a little confusing. Hello? Am I audible? Not sure how that happened.
Yes, Akshit, you are audible. Actually,
Okay.
students are only able to chat. They cannot unmute themselves.
Okay. I'm not sure how my screen it exited on its own, but anyway, I will go to the last slide. Okay. So in this manner, using non-max suppression, you are able to identify which bounding box is the perfect one for the identified animal. Okay. Using this concept of non-max suppression, which uses intersection over union. Of course, I would love to go in more detail to actually code this out and to make you understand every bit and detail. But given the time that we have, I will move to the next slide. In this case, I have some code to present where we will go over some code and try to understand how object detection happens in the real world. Let me share my screen again. Yeah. Okay. So this is a Kaggle notebook that I have that I created for you guys. Since how much time do we have in hand? Can I go on for like 15-20 minutes more?
Yeah, sure, Akshit.
Okay, since we can go on for 15-20 minutes more, I will actually execute the code as we are discussing so that you can see how things are happening in practice. If execution of code takes more time, then I will just go over the notebook. The code is extremely simple. I will tell you the concept and you will basically understand what is happening. Okay. All right. Until this notebook starts, I will start covering what is present in, the code. Okay. Okay, here I can't annotate, but okay, fine. I think I can, select regions to tell you what I'm talking about. Basically, for the purpose of this code demo, I'm going to use a framework called TensorFlow. Basically, to put it simply, whatever we have discussed, you have conceptually understood everything. If I gave you any programming language, C++, JavaScript, Python, anything, any coding language I gave you, you would be able to implement it because you know how things work. But you can't implement things every time, right? Every new project, you can't start from scratch. Some basic elements should already be pre-written and you should just be able to use them into your code and build neural networks. That is what TensorFlow does. There are many other frameworks available like PyTorch, Caffeine, Paddle, and so on, many others. But we will be using TensorFlow because it is easy to understand. We will create our neural network using TensorFlow. Now, since object detection is a common task, TensorFlow has created what is called TensorFlow Hub, where it hosts all types of models, classification, regression, not just images, but even text, all kinds of models. And we'll pick up our object detection model from TensorFlow Hub. Okay, that is what TensorFlow Hub is for. Next, we will also be using images, right, for our object detection class. So for manipulating images, we will use a library called OpenCV. OpenCV is imported in this manner. It is called CV2. Okay. And for other manipulation steps, I'm assuming if you have worked with machine learning and data science before, you must know what NumPy and Pandas is. It is used for data manipulation.
Akshit,
And
I'm
last,
sorry to interrupt. Actually, I can see that you have very low battery in your laptop. Can you just plug it in? If you don't mind?
sure.
Yeah,
Yep.
sure.
Thanks for that heads up.
No problem, Akshit.
Okay. So yeah. And lastly, here, we also have some plotting libraries so that we can plot our images and we can visualize them. Okay. So basically, we will be using TensorFlow to create our neural network, to build our neural networks and build models. We will be using OpenCV to manipulate our images. We will be using NumPy and Pandas for dataset manipulation, and we will be using Matplotlib for image visualization. Okay. Now, I would really love to build the model from scratch. Okay. But we do not have that much time. That would be an entire masterclass in itself. So for the purpose of this demonstration, I will use a pre-trained model. That means I will be using a model that was already trained by somebody else. I'm using their model. Okay. And this model was available on TensorFlow Hub. So I say hub.load and I pass the link to that model. Okay. And that object detection model is loaded when I do that. Okay. It is loaded. Now, if you want, I can share this link with you where I found this model. It is actually open right over here. Okay. I'm using this model on TensorFlow Hub. Okay. And there are several details available over here. For example, if somebody trained this model, which data set did they train it on? If they trained it on, a particular data set, then what were the objects in that data set? So I'll just cover those points. This model was basically trained on a popular data set called COCO. COCO stands for Common Objects, something called Common Objects. I don't remember the exact name, but it was trained on Common Objects dataset, Common Objects dataset. Okay. And when it was trained on this dataset, obviously there were some specifications, right? Like the image should be a certain size, or the image in pixel intensities should be between 0 and 255 and so on. There were certain restrictions. I will be covering those restrictions as well. But more importantly, I want to tell you that this COCO dataset, it has around 100 or so categories of commonly found objects. It is called COCO because it is a common objects dataset, commonly found objects. And these are the categories. So if the model predicts 1, what it is trying to say is that it is a person. If it predicts 2, it is trying to say bicycle, 3, 4, 5, 6, 7, so on. So in this case, there are 91 categories, with the 91st category being hairbrush. So if the model predicts 91, I should know that it is a hairbrush. If it predicts 90, it is a toothbrush, and so on. So that said, I load my model, object detection model. Okay, it is available here. I would be happy to share this link if you guys want to play with this model. Okay. Okay. Now using OpenCV, I'm going to read this image. I have already put that image in my environment. This is the path for that image. And I'm going to read that image, cv2.imread. Okay. Now there are some problems with OpenCV. I will not go into the details of those problems, but the thing is you have to fix the way in which OpenCV reads images. And that fix is done using this line. I will not go into much detail here. What I want you to know is we have our image path and we are reading our image. That's all. And now once we have read our image, I'm going to read the image and I'm going to display it. Now using matplotlib plt.imshow, I'm going to display the image. Now the image that I have selected here is of a giraffe, of a lady who is probably a zookeeper who is feeding a giraffe. Okay, and she has this bowl in her hand and she's leaning over this what appears to be a fence. I can see rocks in the background, there are trees and so on. Okay, and I'm sure most of these objects are present in the COCO dataset. Okay, let's actually quickly view the COCO dataset. So is there a giraffe in this dataset? Giraffe. Yes, I see a giraffe. So if the model outputs 25, I know that it has predicted a giraffe. Is there a person in this dataset? I think I saw person on the top. Yes. If the model predicts 1, it is a person. It has predicted a person. Okay. Similarly, there could be a bowl and so on. I don't know, it must be present over here. But okay, person and giraffe are two main things that I can see here. So when I pass this image, definitely the model will predict, or the model should predict giraffe and person. If the model is working perfectly, it should predict giraffe and person. Minimum. So let's see how that is done. Okay, before we actually use this image to make a prediction, like I said, the image should be in a certain way for the model to make a prediction, correct? Because that model was trained in a particular way and the image should also be fed into the model in that particular way. So what are those considerations that I must know? So one consideration is the image can have any height and width. That is okay. This image has, I don't know, it appears to have a height of around 3000 and a width of 4000. So it can have any height and width, no problem. It could have been a smaller or a bigger image, no problem. But the channel should be last, which means if you remember earlier, I was talking about color images where I said color images are represented as a height cross width cross 3 into 3 cross 3. Why? That is the channel, number of channels, 3 channels, RGB. So the specification that we are given is that the channel should be last. Channel should be last as in height, width, and then channel. That third thing should be channel. Okay, there are other ways of representing it, but it should be like that. And it also says that batch dimension should be first. Now, what does that mean? Now, this image that I have over here is just one image, right? On which I'm making the prediction. I'm using the machine learning model, neural network model. Actually speaking, I could have used maybe 10, 15 or 100 images at once. I could give that to the neural network and in one shot, I could get all the predictions, but I'm using only one image. The dimensions of one image of this particular image are height, cross width, cross channel. So it will be 3000 cross 4000 cross 3. But if I had to make prediction with many images, the dimensions would then be, let's say I want to use 10 images at once. Okay, I'm making prediction of 10 images. Then the dimensions would be 10 cross height cross width cross 3, meaning 10 cross 3000 cross 4000 cross 3. That would be the dimensions. That is the format in which the neural network expects that the image will come. That is the standard format. But since we only have one image, we have to, introduce something called a dummy dimension, which means we have to tell the neural network it is 1 cross 3000 cross 4000 cross 3, which means we are telling that this is only one image. So let's do that. Okay, we will do that, but there are two more considerations before we do that. Second consideration is that the intensities in the image should be between 0 and 255. There is no rule that it should be between 0 and 255, but for this particular neural network that we have read, this particular neural network, this object detection model, it wants the image to have pixels between 0 and 255, otherwise it cannot make a prediction. So we will have to ensure that it is in this manner. Thirdly, the data type must be int. The image, like I said, can have anything, right? It need not have between 0 to 255. It could have even maybe 3000.667. It could have some intensities like that also. But when the specification says that it should be uint, what they are trying to say is that it cannot be a floating point. It can be 3000, but it cannot be 3000.66. 0.66 is not allowed. No floating point, only integer. So these are some specifications that we have to abide by if we want to use this neural network. So let's see which of these specifications are followed by the image and which of them have to be manipulated, or we have to take into account. So we see that the shape is height with channels, which is 3000, 4003, which is good. Channel is last, very good. But batch dimension should be first. So batch dimension is not there only because this is only one image. So we will have to introduce that. Then it says that intensity should be between 0 and 255, which is the case. It is between 0 and 255. Lastly, the data type should be uint8, and that is it. It is uint8 only, correct. Now, how do we introduce batch dimension? How do we introduce that dummy dimension? We use numpy and we say expand dimensions, and we expand the first dimension or the 0th dimension. So this is what the dimensions will look like now. We had 3000, 4003, right? 3000 cross 4000 cross 3. Now we have 1 cross 3000 cross 4000 cross 3. We were able to introduce a 0th dimension, a dummy dimension, so that the model can understand that there is only one image. If there were 10 images, then this would be 10 cross 3000 cross 4000 cross 3, right? You get the idea. Now we can make a prediction. Now let's pass detector of image and let's see the detector output. It is taking some time. Okay, while it runs, I will quickly move to the pre-implemented code, right? So when this detector runs, right, we get some output that is saved in this variable, right? This variable is actually a Python dictionary. Okay, looks like it ran. This variable is basically a Python dictionary. So when I say detector output.keys, it gives me all of this information that the neural network returned. Okay. Now, all of this information is not useful for me. I just want two things basically. One, the first thing I want is what is present. The next thing I want is where it is present. That's all. Only two things. So I want maybe raw detection boxes or detection boxes I want. And I also want detection scores. Okay. Actually, I want three things. First thing I want is what is present, with what probability it is present, and where it is present. Three things I want. So maybe I will use detection class, detection score, and detection boxes, right? So all of this information that is present in this object over here, let me just print it for you to see. And I'm going to say DETECTION okay. As you can see, all the detection scores are present over here, but it is very difficult to read like this, So what I have done is I have put all of this into a data frame so that you can read it very easily. Okay, let me do that. So I have created a data frame to capture the entire output of the neural network of the object detection model. So this output has Ymin, Xmin, Ymax, Xmax. It has detection scores and it has detection class. Now, what is Ymin, Xmin, Ymax, Xmax? You remember I told you that the localization to find out the bounding box, we only need the top left X and Y coordinates and bottom right X and Y coordinates. This Xmin, Ymin, Xmax, Ymax is basically that. It is basically bottom left XY coordinates, top left XY coordinates and bottom right XY coordinates. Okay, so this is what it is. But there is a problem over here. The problem is our image could be of any size, right? Our image is actually very large. It is 3000 cross 4000. But this output is telling us that the bounding box coordinate is at 0.05. So if you look at all other numbers, they're very small. I was expecting that the bounding box would be somewhere here, right? It would be over here. Maybe if the bounding box comes till here, till this lady's hand, it would be at least, around 2300, and it would be around 2000 comma 2300. That would be the coordinates of this lady's hand. But all these coordinates are very small, no? They are only between 0 and 1. Why is that the case? The thing is, when the neural network makes a prediction, right? It makes a prediction between 0 and 1 actually. Whatever be the height and width, it scales it down to 0.1. So the issue is we have to scale it back to the actual dimension. So how do we do that? It is extremely simple. To scale it back from 0 and 1 to the actual height and width, you just multiply the height and width. if you have a number between 0 and 1, and I tell you that the coordinate is at 0.5, okay? Now I tell you, convert this to another system wherein I have an image of height between 0 to 3000. Where do you think that point will be located? It will obviously be located at 1500. If you have 0 to 1 and it is located at 0.5, then if it is between 0 to 3000, it will be located at 1500. So basically, you just have to multiply the corresponding height and width and you get the correct dimensions. So we will do that now. So we have y dimensions, right? Just multiply the height. You have x dimensions, multiply the width, and also make sure that it is integer. Okay. So when you do that, this is what your table will look like. Now these bounding box coordinates are correct. Okay. We were able to solve that problem. But there is one more problem. If you know, because I showed you this website, that 25 stands for giraffe, 1 stands for person. But maybe your management or your business guys do not know that. You have to tell those guys that 25 means giraffe and 1 means person. So you have to map it back. So I have basically created a mapping over here where I have mapped 1 person, 2 bicycle and all that from this website, right? I have that mapping with me and I'm going to use this mapping to clean my data frame. So here I have created a new column, detection object, right? This detection object is telling me that 25 is basically giraffe, 1 is basically person, and so on. Okay. These are the predictions. This giraffe is present at this bounding box. Person is present. This person is present within this bounding box, and so on. It is also telling me that the probability of prediction that this is a person is 0.99. The probability of prediction that this is a giraffe is 0.99. Okay. There are other predictions also. The model has identified bowl also. This lady is feeding the giraffe something, right? She has a bowl in her hand. So the model predicted that also. It predicted the bowl with the probability of 81%, 0.81, right? 81%, and so on. But there is also a chance that the giraffe, the person, the bowl, all of these things, the same thing could have been identified multiple times. Like I showed you the example of zebra, right? Same thing being identified multiple times. It could be the case. So the very first step is to use some threshold and suppress all the less probable predictions. So let's first do that. I'm going to say if the model makes a prediction, I want the threshold to be at least 90%. If the model is at least 90% probable that it is a giraffe, only then you keep. If the model is 90% probable that it is a person, only then you keep. If the model is at least 90% probable that it is a bowl, only then you keep. Otherwise, don't keep. So when you apply that kind of filtering, when you say detection score should be greater than 0.9, you filter out all the bad predictions. Okay. In our case, the filtering was so good that we did not have to, perform non-max suppression. We did not have to use this criteria of, IOU, intersection over union, because we are directly left with 2 predictions, right? So non-max suppression was not required because there are no competing detections for any object. Okay. Now let's visualize these predictions. We have the bounding boxes and we want to visualize where in the image is the person present, where in the image is the giraffe present. So when we plot it using, OpenCV and Matplotlib, this is the output that we have. This red color is the bounding box that says that this is a giraffe. This bounding box at the bottom, this red color bounding box tells that this is a person. So in short, this is how our model was able to predict where is the giraffe and where is the person. Yep. So this brings us to the end of our code. We are also at the top of the hour. So I would be happy to answer any questions that you guys may have, anything that you want me to address.
Yeah, Akshit, there is one question. So how the image matrix of, let's say, 5 into 5 into 1 matrix is convoluted with 3 into 3 filter matrix?
Could you come again? What is the size of the image and what is the size of the filter?
The size of the matrix or the image matrix is 5 into 5 into 1, which is convoluted with 3x3 filter matrix. If it would be better if you just go through the webinar chat.
Okay. There are actually a number of questions I see here. How the image matrix of, let's say, 5x5x1 matrix is convoluted with 3x3 filter. See, this is the exact example that I used in my demonstration. The image is 5x5x1, right? That one is just for representation's sake to say that only one channel is present. Basically, the matrix is 5x5, assuming that we are only looking at a grayscale image, or assuming that we are looking at just one channel, either R, red channel, or G, green channel, or B, blue channel. We are looking at only one channel. So any one channel is 5x5. Okay. Now we have a filter that is 3x3, right? How is convolution performed was covered when I was presenting over here. So this is a 5x5 image, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is a 5x5 image, and this is a 3x3 filter, correct? If you want to say, for the sake of argument, this is a 3x3x1 filter, because there is only one filter, right? If you were considering an RGB image, there would be 3 matrices, one behind the other. Similarly, there would be 3 kernels, one behind the other. In that case, it would be a 5x5x3 image and a 3x3x3 filter or a kernel. That is how it would be. This example that I covered here, I think it addresses your question. You can definitely maybe go back to this recording, and maybe you can get a better picture. Let's see. Are you using Python? Yes, this is using Python. The programming language that I have been using from the very start was Python. No other language was used. TensorFlow is a framework developed using Python only. Even OpenCV, NumPy, all these are frameworks that were developed using Python. It's pure Python. Sir, what would CV2 does? See, CV2 is OpenCV. Okay, OpenCV is a project for manipulating images. Okay, it is a computer vision project. CV means computer vision. It is a project for manipulating images. So we have imported that library, that package, and we are using it to read the image. We have also used OpenCV or CV2 in order to plot the bounding boxes. Like, I wanted to plot a rectangle, right? And I also wanted to plot the text. So this red color rectangle and this text, giraffe and person, that was also possible using OpenCV only.
Yeah, Akshit, there was one interesting question from a student.
Yeah.
What is the use of object detection in data science?
What is the use of object detection in data science? So what is data science? Let's try to see first. In data science, we have data, which could be text, it could be images, it could be tables like your Excel sheets, right? It could be speech, like I'm saying something right now. It could be a video, what we have right now. All of these are data. And data science is basically a field wherein we study how to work with these data, right? And what we just looked at are image data. Images are also data, right? So they fall under the domain of data science. And we're trying to see through object detection how we can extract some information present in images. If I give you an image, can you tell me what is present in that image? Yes, you can, using image classification. Can you tell me where something is present in image? Yes, you can, using object detection. So object detection is as such like a subfield of computer vision that helps us, understand what is present where and where it is present in an image. I hope that answers your question.
Yeah. So one last question, Akshit. So is there any other algorithm other than CNN to perform object detection and image processing tasks?
This is also a very good question, actually. So I want to make it clear in this webinar that all of this convolutional neural network example that I have used is just one way of doing is just one way of building an object detection model. There are many other ways of building object detection models. Firstly, like I said, this is not the only architecture that is used for performing convolutions and pooling. There can be many others. Some researchers have gone to the extent of saying that, you know what, we can do away with convolutions. Let's not use convolutions. Let's use something else instead of convolutions. For example, vision transformer. So vision transformers are an alternative to convolutions that can be used to process image data. So it's possible, but the more common thing is convolutional neural network.
Thank you so much, Akshit. So thank you so much, Akshit, for your time. You have given wonderful insights to the students on object detection. So that's it for today, guys. Thank you all for joining. See you guys in the next session. Thank you so much, Akshit, and thank you so much, Mr. Vijay.
Thank you for having me.